Hello, this is your grumpy old middle school science teacher at school. In my career in science education, I've learned a lot about how to teach science and some of the problems we have in getting science concepts across to the average person. Early in my career, I was exposed to a video called The Private Universe. This video is now available. You can watch it, stream it online. I'll put a link to it in the comments below. Private Universe taught me that even though we have improved our techniques in teaching science, a lot of people, even at the college level, don't grasp some basic, simple science concepts. And it asks the question, why? What are we doing when we teach middle school, high school, and even in college, that so many people don't grasp basic science concepts? And as I've struggled with this over the years as a classroom teacher, a college professor, a curriculum coordinator for a large suburban school district, I began to come up with the idea that one reason so many people don't carry their science knowledge out of school, don't become science literate, as it were, is that we don't build a big framework for which they can put their science learning. Now, if you go on YouTube or any other social media, there are some incredibly talented, intelligent science presenters. And they present some fascinating facts, and I enjoy watching them. And what I see there sticks with me because it resonates with what I know about science. But I recognize that for a lot of people, these are just factoids. They're little bits of information that they're fun to know, but don't necessarily remember because people don't have a framework to hang this learning on. So what I would like to do on this channel, called Old Middle School Science Teacher, is to give a lesson, a class in the fundamental nature of science to help you as a science educator, as a member of the general public, really begin to understand science in a way that allows you to detect when things are claims without data, to reject some claims that are bouncing around now that make absolutely no sense if you understand science. Now, in the beginning of our journey, there are a couple of things that I want to put out there as fundamental concepts. First of all, science became science when scientists realized that we lie to ourselves. I'm going to say that again. We as humans will lie to ourselves. When we see something and we become convinced that our observations are valid, we are very, very hesitant to change those ideas. Scientists realized a long time ago that a bunch of observations don't always lead to truth. Carl Sagan, in his book, The Demon Haunted World, does a good example of explaining why that if you're living in the safari in Africa and you begin to suspect that rustling in grass is a tiger that's about to eat you, all of the time that there is no tiger, but there's a rustling in grass, but you think there is a tiger, it doesn't hurt you. But if you ever stop thinking that there might be a tiger in the grass and there is a tiger, well, it could be the end of your line. So we tend to believe false positives. What scientists begin to realize is we need to understand that we will lie to ourselves, that we have bias. That's the term we use in science, that we have bias. And we try to design our understanding of the universe in such a way that we can counteract this bias. You've probably heard things like double-blinded studies, control groups, experimental design, data. All of those things are the scientific way of addressing bias. They had to collect data. They had to analyze that data. they had to share not only their conclusions, but share their data and their procedures with other people. Because only then can other people critique and decide if your conclusion based on your data is valid. Scientists love to argue. Scientists would like nothing more than to conduct an experiment and find new data that could overturn some long-held belief in science. But over time, as data is collected, conclusions are drawn, other people look at the experimental design, they look at the data, they look at the conclusions, and they argue. We began to come to true understanding of how the world works. That's science. Scientists don't always agree. But what science do is we engage each other in dialogues. That's why when you read an article or read some new claim, the first question you got to ask is, where was this published? Was it published in a popular journal about science? Was it published in a just popular media? Or was it published in a science peer-reviewed journal where that article went to a group of other people in the field who can critique the procedure, the data collection, and the conclusions drawn from that data? And then is it put out there for the body of scientists who read those journals to analyze, to evaluate, to make suggestions, to argue whether they think that is correct or not? So one of the first things that we're going to say in our study of science is, show me the data. Show me your procedures, how you collected the data, how you controlled for biases. Show me your numbers. Present your numbers. Tell me what your conclusions are. And then let the rest of the scientific community analyze what you've said and come to consensus. Scientists don't always agree completely on everything. But over time, as more and more data is collected, more and more experiments are run, more and more conclusions are articulated and explained, we began to come to central truths. We even have a process now in science called meta-analysis, where we go back and look at multiple studies on the same subject. And we evaluate the strength of all of those studies to come up with what the fundamental conclusion is. Because we do get studies, especially in the social sciences, where some data goes one way, some data goes the other way, but over 20, 30, 40, 50, 60, 70 studies, the preponderance of evidence will tell us what the science is. That's one of the big differences between science and pseudoscience. Pseudoscience does not often articulate their procedures or their controls or how they're accounting for bias. They don't always share the data. They don't publish in peer-reviewed journals and allow other people to look at their data and their experimental design and point out flaws and weaknesses and allow us to come to valid conclusions. So the number one premise in science is, show me your data. Trust but verify. What are the facts? How did you collect them? The second thing that science is based on is a belief that scientific laws are the same throughout the universe. What that means is, if we discover a law of nature, and a law of nature we'll go into more detail in future videos about the different things like hypothesis, guesses, laws, theories. But a law of nature is a basic principle that happens. We can observe it, we can measure it, we can usually mathematically model it, but we know it takes place. Now, there are people who want to argue about certain scientific laws. The law of gravity has been around 300 years. Now, the theory of gravity is a whole different ballgame. We'll talk about that later. But the law of gravity simply states that any two objects that have matter are attracted to each other based on the mass of the two objects and what we have discovered, a universal gravitational constant. So when we say the laws of nature are the same throughout the universe, what we're saying is that the law of gravity is the same on Earth as it is on the moon, as between the moon and the Earth, as it is on Jupiter, as it is on the next star closest to us besides our sun, that is a fundamental law of how the universe works. And if the laws of nature are uniform, universal, then what we learn here we can apply in other places. Those are the two big fundamental concepts that allowed science to become science. We can trust that the gravitational attraction in Dallas, Texas, in New York City, in Tokyo, on the moon, on Mars, they're all controlled by the same law of gravity. Now, in all my years in dealing with teachers, and I spent 22 years as a science director for a large suburban school district. I have trained teachers at the collegiate level. I've mentored many, many teachers throughout the years. I've presented staff developments at the district level, the local level, the state level, even at the national level. What I've learned is that very often we put teachers into classrooms who are not prepared. And I'm not putting down any teachers. I'm one of you. I spent the last 5 years of my career as a classroom teacher. But when I look at the kind of training that so many teachers get before they enter the classroom, it doesn't surprise me that they have difficulty creating big pictures for students in their classrooms. I've met some phenomenal biology teachers. They understand biology in and out, but what they don't understand is how biology related to physics relates to chemistry. I know some great astronomy teachers. They usually know how astronomy relates to physics, but do they understand how it relates to chemistry and biology? All the sciences are interreacted. Physics, chemistry, geology, astronomy, those are just terms that we've put on different areas of study. But the underlying science is the same for all of them. And once you begin to build that intellectual framework that lets you see the connections and how chemistry depends on physics and how biology depends upon chemistry and physics and geology depends upon biology and chemistry, once you begin to make those connections, it's much easier to learn science. Now, we are in an amazing time with social media where we have all kinds of really phenomenal science educators, from Bill Nye, or when I was a child, Mr. Science, but to Bill Nye, to Hank Green, to the guy with Veritasium, to hundreds of other people out there, and I know I've left out a bunch of them, and I apologize, that are really doing a great job explaining science. Just recently, I've stumbled across a number of medical doctors who are doing their best to share the medical research that impacts our health in a way that's accessible to the average person. But what none of these educators are doing, that I can tell, and I may have missed one, is trying to start at the basic level, middle school science, and explain how all of these sciences fit together. So that when you go to talk about a new medication and the functional activity of a drug, you can relate that to the chemistry and the physics behind it that cause it to happen. So what I want to do in this series is I want to help educators, lay people, understand the fundamental framework of science. I think of it like building a bookcase. The other science creators I see on social media, they're giving you lots of factoids, but where do you put them? What I want to do is I want to help you build a big bookcase so that it all makes sense and you have cubby holes and pockets to put all the different concepts so that they make sense and you can understand how they relate to each other. Now, to do that, we're going to start at the very beginning. I'm not going to do a historical approach. Sometimes I think we overdo that. We're trying to prove why we believe what we believe, so we go back and start talking about Isaac Newton and the Michael Morrison experiments and Einstein's theories. What I want to do is I want to talk to you about the fundamental concepts that underlie science. As a curriculum director, we studied the work of Grant Wiggins and Jay McTighe in Understanding by Design. And in their curriculum framework, what they say is that for any subject area, there are some enduring understandings, big ideas that underlie everything. And that if we don't express those big ideas to kids and help them gain those big ideas, then all we're doing is teaching them a bunch of little facts. And that we can't retain the little facts. We need the structure. And so in working on curriculum and with curriculum writers and teachers, I kept coming back to the same two big ideas underlying science. And it finally hit me that these big ideas are the hinge pins, the foundation of how we understand the world and how it works. And so we're going to start with these two big ideas. The first big idea is that all matter is composed of atoms. Now, that's easy to say, but a little more complicated to understand. Now, for you physicists out there who want to come at me with quantum mechanics and quarks and all that kind of stuff, we'll get there, we'll touch that. But for right now, let's just start with all matter is composed of atoms. I know, technically there's matter in the universe that is not in atomic form. There are free electrons, there's all kinds of stuff. But we'll get there. But a good framework to start with is all matter is composed of atoms. Remember, I'm your grumpy old middle school science teacher. The second concept, once we've established atomic theory and the nature of atoms and how that impacts so many things that go on, we're going to look at the law of conservation of matter and energy. And what it says is that matter and energy can be transformed, but they cannot be created or destroyed. Now, once again, for you advanced science people, don't come at me. I know we can turn matter into energy and energy into matter. But fundamentally, the amount of matter and energy in the universe is a constant. It's called the law of conservation of matter and energy. We're going to start with those principles, and we're going to build off those principles and show how those principles will help us understand physics, chemistry, biology, geology, astronomy, the whole gamut of the scientific fields. So, I hope you'll join me. I've got to apologize. This is my first time cutting a video and doing YouTube stuff. So the audio may not be great. My background's not perfect. But I'm here to provide information in a way that hopefully you can grasp. And it'll help you, one, be a better science teacher if you're a science teacher, or be more scientifically literate if you're not. Signing off, your grumpy old middle school science teacher. I hope you'll join me for a fascinating journey into the nature of science.